Welcome. Thanks for joining us for today's presentation. We're going to be talking about the cozy load balancer on the zEnterprise. Today's agenda covers the following. We'll first of all discuss the zEnterprise environment that we're going to be demonstrating the load balancer on. Then we're going to give you a brief overview of what we refer to as z/OS hybrid batch processing. Following that, we'll go through the cozy load balancer features and requirements, and then give you a live demonstration of how the cozy load balancer operates in this environment with the cozy coprocessing toolkit and the zEnterprise ensemble. And then finally we'll finish up with a summary and some observations. The zEnterprise environment that we're running on is configured with a zOS partition running v1r13. We have on that partition a copy of IBM's SDK along with JZOS, which is part of the SDK, which we make use of in the load balancer. We also have installed on the zOS system IBM's ported tools for zOS, of which we make use of both the OpenSSH and curl components. And we also have installed the cozy coprocessing toolkit and of course the cozy load balancer. On the ZBX array we have the following configuration: 2 Linux blades, 2 AIX blades, and 1 Windows Server blade. And we'll show you how those all interact a little bit later on. And finally, on each of the virtual servers installed on the blades, we have the following software. IBM's GPMP, which is required for reporting load statistics through the SASB interface, which we'll talk about in a little bit. We have also installed on each of these virtual servers a Java SDK, which will support some of the work that we're going to run on these virtual servers. We have a small portion of the cozy coprocessing toolkit on each of the virtual servers called the Target Systems Toolkit. This is a little bit of a management program that runs and coordinates the work between the zOS batch job stream and the remote system. And then finally, on the Windows Server machine, we have installed Cygwin, which is used for implementing and running its version of OpenSSH. Okay, so before we get started in talking about the cozy load balancer, I would like to take a little bit of time to discuss the impetus for actually having the load balancer in the first place. And to do that, I want to take a step back and introduce a term that we've been using to describe the relationship between running zOS-related work on remote systems. So we've coined this phrase zOS hybrid batch processing to describe what's covered in the following five bullets. So in other words, if we can achieve these 5 things, then we have what we would refer to as a hybrid batch processing environment. So the first thing is we have to have the ability to execute a program or a script on a distributed target system from a zOS batch job. Not from Unix system services, not from TSO Interactive, but from a batch job stream itself. Secondly, the target program that we're executing may already exist and probably does, and it should require little or no modification in order to run in this environment. Thirdly, the target program's input and output are automatically redirected from and to zOS spool files or data sets. Namely, we mean the standard streams for this program. Standard in, standard out, and standard error should be redirected back up to zOS so that they can be examined by zOS operations staff rather than having to have them search on the remote systems for this information. Fourthly, the target program may access other resources in the course of its work. It may reach back into zOS to read DDs that are defined by the job itself. It might read data sets that are separate from the job It might read Unix files, and in fact it might even run ZOS Unix programs in order to accomplish some of the work that it wants to complete. And finally, the target program, when it finishes, its exit code should be adopted as the ZOS job step completion code. So with those 5 things in mind, we have what we refer to as ZOS hybrid batch processing. Okay, so if you think about that for a minute, what we have is an environment where ZOS is requesting that work be run on a remote target system, and then within the control of that job stream, waits for that work to complete, and then adopts the completion code and continues on its merry way. A logical question is raised that says, well, how do I dispatch work to one of these virtual servers? What if one of the virtual servers is heavily loaded and I don't want work to go there? I'd rather have it go to someone that's less heavily loaded. Well, of course, we can always specifically target an absolute or real virtual address for one of these servers, or we can have some kind of load balancing feature that dispatches work to the available virtual servers based on their workload. And that's effectively what the Cozy Load Balancer does. So the way it does it is that it's integrated very tightly within the zEnterprise ZBX architecture. It implements the Server Application State Protocol, otherwise known as SASP, and it directly talks to IBM's zEnterprise Unified Resource Manager, or the ZURM. And as I mentioned earlier, it distributes hybrid batch work to available ZBX virtual servers. The servers themselves can be configured into groups using an XML configuration file, and the groups are validated using a group confidence quorum, which basically says that in order for a group to be valid and dispatchable, the individual servers in the group we have to have a certain number of those responding to the ZURM with their weights and loads so that we can dispatch reliably to them. And we'll get into that in a little bit. When the load balancer is deployed on ZOS, it doesn't have to be, by the way. It can be run on a system that's not ZOS. But when it is deployed on ZOS, it integrates closely with the ZOS console, including write-to-operator logging and messages, and it supports console commands for restart and shutdown. And then finally, the load balancer itself offers a web service, just a simple HTTP protocol for retrieving status advice, meaning what virtual server to choose next for the next piece of work, restart and shut down. Okay, so let's move on. In terms of the software stack required to support the load balancer, we need the following things. We have to have on ZOS, we have to have IBM ported tools installed, and for that, and of the ported tools components, we're using the curl component for retrieving status from the load balancer. We also need to have the Cozy Launcher installed on ZOS so that we can actually dispatch and coordinate the work with the virtual server. And for each virtual server running on a ZBX, we need to have one of the IBM supported operating systems, including AIX on P, Linux on x86, or Windows on x86. On each of the virtual servers, as I mentioned earlier, we have to have GPMP installed, and that's part of the zEnterprise installation. You just need to manually install it and make sure it's operational. And then finally, we have to have the Cozy Target Systems Toolkit. And for the system running the load balancer itself, the load balancer is written in Java. So on ZOS, if you're running it there, you of course need the IBM Java SDK. And if you're running on a non-ZOS platform, any Java SDK at version 6 or above is okay. The load balancer was released in May of 2012 and is available for free use using a community license, and it's also covered by our support contract for our gold level support customers. For product documentation and download, here's a URL that you can visit and get some more information. Okay, so before we actually look at the load balancer running live, I want to throw up a diagram here that describes the ecosystem in which the load balancer operates. So on the left side of the diagram, we have a picture of our ZOS system running on a zEnterprise, and at the top we have the Cozy launcher. And this Cozy launcher, there can be multiple instances of the launcher running in multiple job streams. And what the Cozy launcher wants to do is it wants to dispatch work to one of the target systems on the ZBX array, which is on the right-hand side. So you can see the list of virtual servers over there, Linux, Windows, and AIX. So in order to figure out what target to use, and I'll just sort of highlight that here, which target to use, we can, as I mentioned earlier, we can either explicitly code the address of one of those virtual servers, or we can ask for advice from the load balancer. Now what the load balancer will do when it's asked for advice is it will communicate with the HMC in the zEnterprise environment and talk to the ZURM and over this SASP protocol and ask for the virtual server that best fits the work request based on their relative workloads. So you imagine this: the Cozy launcher wants to do some work. It asks the load balancer for advice. It gets the advice back, and what comes back across this stream is the IP address of the server that was chosen. The Cozy launcher then takes that IP address and plugs it in and dispatches work to that particular virtual server. So from a high-level perspective, that's what we expect the load balancer to do for us. Okay, so let's get right into a live demonstration of how this all works. And to do that, we're going to cover the following items. We'll look at, first of all, the configuration file for setting up the groups, virtual server groups, for our load balancer. Then secondly, we'll take a look at the web interface for the load balancer and look at the status, that is the group status, and then run some advice testing to see that we can actually see these virtual servers coming back as requested. Then we'll move on to actually doing some real work. We'll run some work from the Cozy launcher using the load balancer to dispatch the work to a particular virtual server. And we've got a couple of examples that we're going to show here that explain a little bit about how the launcher works and what it does, as well as how the load balancer hooks into the whole process. Then finally, we'll take a look at what's been showing up on the ZOS console, so you can get a sense for what's happening there from an operations point of view. And we'll shut down the load balancer using our console interface for doing that. Okay, so before we look at the screen, let's take a look at a configuration file for the load balancer. This is a very simple XML document. It consists of a root level element called config, and config, the element itself has three attributes. The first attribute is the load balancer UID, and this is required by SASP and required by the ZURM to uniquely identify this particular configuration. So we call this LBUID Cozy-LB01. The next attribute is the group workload manager server, and that's the address, the IP address of the HMC itself, and that's hard-coded right there. And then the third attribute is the group confidence quorum %, which we have set at 50. And what this effectively does is it says that that at least one half of the virtual servers in a given group have to be reporting in with valid and verifiable weights in order for us to trust dispatching weight advice from the load balancer. Okay. Following this outer element, we have two groups defined. The first group is called ZBX group, and it, as you can see, contains the two AIX virtual servers and the 2 Linux virtual servers, each with their host IP address and the port that they're going to be listening on for work. So we're listening on SSH on the SSH port 22, and then each of these servers is given a standard or starting default weight, which we've set to be 60. So they're all going to start out at the same weight until we actually start getting back load reports from the zURM. The second group has a single server in it, and this happens to be a Windows Server virtual machine, and we put it in its own group just to show that we can set up multiple groups. We call that group the Win group. Okay, so I want to before we actually talk to the load balancer, I want to show you the JCL required to kick it off. This is actually very simple. It's a very simple JZOS job. For those of you familiar with JZOS, it's a component of IBM's Java SDK, and it allows us to communicate to basically run Java from a batch job stream. So the only thing of real interest here is the class that we're going to start, which is com.dovetail.cozy.saspi.loadbalancer, and the arguments to the load balancer are, of course, the configuration file that we just looked at. What follows in the rest of this JCL is basically the setup, pointing us to the installation where the load balancer lives on ZOS Unix System Services. We cd to that directory, and then we set up a bunch of environment variables and kick off our Java job. Okay, so the next thing I want to do is show you the actual status and advice from the load balancer, and we can do that by using just a regular browser. So what we do is we just put in the address of the host that the load balancer is running on, and that's my host name for that is ZENTZOS, ZENTZOS. The port that the load balancer is listening on, and in this case it's 8860, and then we simply call the status HTML page. So I'm going to go ahead and run that, and you can see that we've updated our screen here. I'll run it again just so you can take a look in particular at the weights. You might see them change as I refresh the screen. They may not if the loads have not changed. But here's a report, and we can see a couple of interesting things. The Windows group, which has just the Windows server in it, is reporting no quorum, 0%. And what we can see about the Windows group is that we have some information from that Windows server that we've registered with it, but we haven't contacted it, and we are not confident at all about the results that we're getting back. So, in fact, this Windows virtual server is down. It's actually not even running right now, so we're not going to get weights back. So this is one way of knowing that we are not going to get valid weights back from a particular group. The second group, our ZBX group, contains our 4 other virtual servers, the 2 AIX and 2 Linux systems, and they are all participating. We can see that our quorum is in fact 100%. So they're all registered, they've been contacted, and we are confident that the results that we're getting back are actually results that have been verified by the SASP interface. So I'm going to run this again, and we can see that there's not been much change. I should point out, for the purposes of this demonstration, I have actually started a fairly intensive workload on one of these virtual servers. It happens to be the first Linux blade, and you can see that its weight is reporting back as a weight of 5. The other 3 servers in the group have significantly higher weights relative to the one that has a heavy workload on it. So you can see that the 2 AIX servers each have a weight of 74, and the second Linux server has a weight of 71. So conceptually, the lower the weight, the less likely we are to select that server for future work, because the lower the weight means that it is already more heavily loaded and is therefore less able to take on new work. So let's actually take a look at that and note that we have IP addresses from 172.29.255.117 through 120. So what I'm going to do next is I'm going to show you the advice interface to the load balancer. And this is very simple. What we do is we, again, talk to the load balancer host at port 8860. And this time, rather than asking for status, we ask for advice. And then, of course, for advice, we need to supply the group that we want to get advice from. So in this case, we want to get advice from the 4 virtual servers in the ZBX group. And if I run this, take a close look at the target host that gets returned. You should see that change as I run this a couple of times. So there, we're at 117. I'm going to run it again, and we get 117 again, which is okay, and we'll explain that a little bit later on. If I run it again, you see that it is now cycled to 120. So it's a fairly random, distribution to a certain extent, but you'll notice that we didn't see 119 show up, and we'll explain why that is as we move forward. Okay, so that's the example of how we actually get advice from the load balancer. Okay, this is a shell script that is used, and we'll see how the Cozy launcher uses this shell script in just a little bit. But this shell script is used, you can run from ZOS Unix System Services to talk directly to the load balancer to actually get that advice. So you can see here that the invocation is that we call advice, the advice.sh, and we give it the group name that we want to get advice for. And the script does a couple of things. It sets up a pointer to our installed path to curl, and then we specify the load balancer host and port. And then the meat of the script is essentially just a simple curl call, that is to retrieve a web page from the load balancer host at load balancer port, and we want the advice web page results having passed in the group name, and that's $1. That's the first argument to this script. So effectively, this is a programmatic way of asking for that same advice page that I just showed you. Okay. So let's look at a simple example of invoking the Cozy load balancer from a Cozy launcher job. This is actually quite simple JCL. We have our job card. We have a proc-lib that points to the PDS that we're running in, and we at the beginning of this first job step is to invoke Cozy proc, which is a JCL proc used to invoke the Cozy launcher. Secondarily, we have an input DD defined, and this is just a test DD to kind of demonstrate some of the Cozy launcher features, and it's simply referring to a member, some random member in sys1.maclib. We're actually going to be looking at the ACB member here. And then finally, we have, actually not finally, but next we have the configuration for the Cozy launcher itself, and that's in this Cozy CFG inline DD. So there's a couple of interesting things here. These are properties that we are going to specify. The first property is the target user. That is, this is the user on the remote server that we're going to ask to perform the work. And then rather than specifying a target host explicitly, which we would also be able to do, we're going to do this. We're going to specify a properties exit property, and the properties exit is basically going to explicitly call that advice script that we just looked at, passing in the group name of the virtual server group that we want to get advice for. So under the covers, what's going to happen is this properties exit is going to go out, run that script. It's going to get back the IP address and the property name of the of the server that we want to use, and then that's going to be the IP address that we direct our work to. A couple of other things. Because we're running in a zEnterprise environment against ZBX blades, we can transfer all of our data over the Inter-Ensemble Data Network, the IDN. And we don't have to actually tunnel that data back through SSH because we're already on a secure network. So we can speed things up by setting this SSH tunnel equal to false, and then setting the server host back to our ZOS system so that we know where to communicate when we want to tunnel that information, when we want to retrieve that information. Then finally, we have the input to the Cozy Launcher itself. And this is a very simple invocation of the Cozy Launcher. The first thing we do is we run a simple echo command from the shell to write out hello and then the host name of the target system that we happen to be running on. And the second line of the shell script does some interesting things. We'll walk through this very briefly. The first thing it does is it uses a Cozy dataset pipes utility called fromDSN to read from DD input. If you remember, we defined that to be this ACB member of the sys1.maclib. It reads that input in binary. It pipes it to gzip in compress mode, where gzip will compress that data, and then it pipes the result of that gzip compression to another dataset pipes utility called toFile, which in binary writes the output to /tmp/out.gz. Now, the question is, where is this tmp out.gz file? Well, it's on ZOS. Even though this program itself is running on the remote system, by using these dataset pipe utilities, we're actually reading data from ZOS, from sys1.maclib, running it through a utility gzip, which is running on the remote system, and then writing the information, the compressed data, back to ZOS using this toFile command. So let's go ahead and take a look at that. We'll actually invoke that this program and see how it runs. So to do that, I'm going to find our LB hello member. This is the JCL we just looked at. And I'm going to go ahead and I'm going to submit that job. And it will run fairly quickly. It doesn't take too much time to set this up and complete. You can see we've completed with a condition code of 0. And now let's take a look at our job in the output spool. Okay, so there's a couple of things we would like to look at. First of all, let's take a look at the standard out from the job itself. Well, it says hello AIX B20203, and this indicates to us that what has happened is that the load balancer has identified the second AIX virtual server as the recipient for this work. Okay, let's further confirm that by looking at our Cozy log. And you can see that down here in the last line, the Cozy launcher says that it's that the target command was run on the server 172.29.255.118, which is that second AIX virtual server, and it was run by Cozy user, and it completed its job with a return code of 0. What's also interesting in this Cozy log output from the launcher is you can see that our standard in, that is the shell script that did the echo and the from DSN, was read down to the target program. It was 2 records in length. The shell script was 2 lines long. And then the shell script went and retrieved its input DD, that is the data from the ACB member of the sys1.maclib. That consists of 78 records, and it read that down to do its processing. And then finally, we can see some logging information from our toFile command, where we write to the ZOS temp directory, this out.gz file, and the compressed data consisted of 1,419 bytes written back to zOS. And then finally, to kind of round things off, we see that the target program's standard out and standard error are being sent back to zOS, and we just looked at the standard out just previous to this. So what you have in this screen in a nutshell is a real life example of zOS hybrid batch processing. There's a program that runs on a target system. Its standard in, standard out, and standard error come from zOS and are sent back to zOS, and it is able to reach back into zOS to retrieve data sets and DDs and or write to, for example, zOS Unix files. And then finally, the RC0 is adopted as the job step completion code, as we saw when our job completed. Okay, so that's an example of a very simple example of running the Cozy launcher with the load balancer. Now, what about something a little bit more involved and interesting? That's kind of a play example. Let's take a look at something that is more involved and is more suitable to being dispatched to a target system. So imagine this. Imagine that you have an environment where you want to send letters to a whole list of customers that you have in a database somewhere on your zOS system. And let's say it's a form letter, and you want to use some kind of mail merge mechanism where you have a PDF portable document format template that you want to plug into. You want to plug in the address, unique address information, and name, salutation to the person corresponding to a row in your database. So this would change. So you imagine you might have thousands of these letters that you want to send out, and the content is the same except for example, the address and the name. Let's say further that we might actually have some fields that are constant across all the letters, but might change from run to run. For example, our date field. So think about this information as common data and common fields, and think about this as field data and the fields that we want to change on each particular version of the document. So this is something that we could run on Java for zOS, and there would be no problem doing that, except for the fact that in some cases zOS Java doesn't perform as well as we would like. We'd like to maybe run this faster, or we'd like to unclutter our zOS system and move some of this work off to a virtual server where we can offload the work. So let's look at the JCL required to do that. Again, this is a little bit more complicated this time, but if you focus first of all on the center of the JCL, the stuff that's bolded, you can see that we have our Cozy launcher configuration, again as we did before. We specify our target user, which is still Cozy user. We're going to use the load balancer to get advice to determine which virtual server we're going to run, which of those four systems we're going to use. Then we turn our tunneling off, and we have our server host identified so that we can speed up the data transfer between the zOS system and the target system. So that's the same as it was in the previous case. Now, what's changed is, notice that at the top here we're still invoking the Cozy launcher via Cozy proc, but in this case we have a lot more DDs defined. We have a DD defined for the field data. That is, this is going to be the data that we're going to change on a per row basis based on what we've read from our database. We have the field map. This is the map of fields inside the PDF template that we're going to use to replace that data with. And then we have similarly common data and common map, which are for example, in our example, the date fields that are going to be the same for every one of the documents, but will change each time we make a different run. Finally, we have a DD that points to the PDF template itself, which is located on our zOS system. And we have a DD that refers to where we want the finalized PDF to be written. This is going to be the composite PDF that contains one document for each one of our users in our database. So this DD exists on ZOS as well, and you can see that we have defined a DCB and disposition information for it. Okay, finally, we have the job itself that's going to be dispatched to the target server. And this is a call to another Java program, and its name is com dovetail cozy iText PDF generator, and it takes the arguments that we referred to before: common data, common map, field data, field map, the PDF template, and the PDF output. Okay, this is where it gets interesting. So for a Java program, you typically would supply a file name for each of these arguments. In our case, what we're going to do is we're going to use the dataset pipes utilities to read from ZOS. Remember, we're running on this remote server that's not actually running ZOS, it's just running Linux. We're going to reach back to ZOS, we're going to read the COM data, and using this syntax, this bash syntax, the left angle followed by a left paren, we're going to use a feature called process substitution, which basically is Bash's way of under the cover setting up a FIFO on the target system, and that allows our Java program to read from that FIFO as if it were a local file, even though the data itself is coming from ZOS. So you can see that we're setting up read FIFOs for all of our input data, and then the output data we're setting up a write FIFO, and that's specified using the right angle bracket followed by the left paren, and again using this process in Bash called process substitution, where Bash will set up a pipe for us that looks like a file. Okay, so without spending too much more time on the JCL, let's go ahead and see if we can invoke that from on our zEnterprise system. So I'm going to go ahead and locate that JCL. It's called LBI text. And you can see again here, this is what we just talked about. Let's go ahead and submit this job. So it's going to run. It takes a little bit of time to run, and it completes. And we can again take a look at our output to see what's going on here. First thing I'll do is I'll take a look at the job's standard error, because this is where some interesting things can be viewed. Here's the output from the Java program itself that's running on the virtual server. And notice here's our argument, common data, but notice what's happened. That process substitution has been replaced with what looks like a file name, and in fact is a file name, /tmp, and then some weird name that's generated by Bash. So the Java program just thinks it's opening and reading from these files to get this information, and on the output, the PDF output, it thinks it's just going to open that file and write to it. But when it writes to it, since we've done process substitution, it's actually going to write all the way back to ZOS into that PDF output DD that we defined in the job. So the rest of this information is just information about the job run. And looking again at the cozy log, this is very similar to what we looked at before. You can see that we, in this case, ran on target system 118 again for this particular run, and we used our from DSN and to DSN utilities to communicate with ZOS. Now let's go ahead and submit that job again to see if we can get a different virtual server this time. I'm just going to run it one more time. There, it's completed. And let's take a look at this job. And it's picked 118 again. So in this case, we're just randomly selecting that that first server. Remember, this one has a lot of, these servers have fairly high weight levels, so they're going to be picked in general more often than 119, which is heavily loaded. So if I were to run this job multiple times, you would see different servers selected based on the call to advice. Okay, so let's start to wrap up here. The Cozy Load Balancer, as I mentioned before, is connected to the ZOS console, and as such, it supports a couple of commands. We can restart it if we've re-changed our configuration and we want the load balancer to adopt the new configuration. That is, maybe we want to add some servers to a group or remove some or add new groups. To do that, we would just issue a modify command to the running job and then issue a restart request. Or if we're finished running, we can simply shut it down and wait for it to finish from the console. So I'm going to do that. I'm going to first of all switch over to our log, and we then issue a stop command to the Cozy Load Balancer. And you see it came right back and it finished. And if we look at our console log, you can see that we received a stop command, and then as a result we shut down our SASB connection, stopped the client, and then stopped the load balancer itself, and it all completed as we would expect. Okay, so let's go ahead and move to the next chart. Now, when I ran those two iText jobs, notice that I ended up on that first AIX, the second AIX server a couple of times. Let me explain how that happens and what's going on here. So if you take a look at this graph, it shows the relative workloads of the virtual servers that are running at any given time. And you notice when we showed our status, we had one server that was reporting a very, very low weight number, and that's this first Linux server. It was reporting a number of around 5. So if you think about that, that's where we were. We were right. This is the beginning of when we first started the load balancer, and as the load to that server continued, its availability for being selected and its suitability for work continues to decrease until it reaches this point where it's really not likely to be selected at all. So in terms of how we select, how the load balancer selects what server to run on, we use the following algorithm. Think about this entire span from the start of the 0 on the y-axis all the way to 100% on the y-axis as the total cumulative sum of all the weights of the servers in that group. So if you remember, we had 2 that were at 74, 1 was at 71, and 1 was at 5. So you add all those numbers up and you come up with a grand total. And then what we do in the load balancer is we just generate a random number anywhere from 0 to that grand total. And whatever that number is, we starting at 0, we just index into our stack of server loads, and wherever, let's say we generated a number 10, it would land right about here, and we would pick the AIX1 server. If we generated a number of, say, 90, 74 gets us past the first server, and then we land square into the second one. So in our examples, we were generating a number somewhere between 74 and say 150. To get us onto that second server. And so you can see that based on the relative weights, that as we generate a random number, we might in fact end up on this Linux 1 blade, but it's like the likelihood of actually landing there is significantly reduced. So again, as you watch this workload over time change, you'll see that the load balancer is going to return suitable servers for work based on the relative weights that they're reporting. Okay. Now this is just a line graph of the previous chart that shows over time what happens to the weights that are reported back from the ZURM and this SASB interface based on the amount of work that's happening on any given or all of the virtual servers in the group. Okay, so that's pretty much how the load balancer works and how it ties in with the COSY launcher. I want to summarize for you briefly before we finish up. If you take the COSY launcher and add it into a zEnterprise ensemble, what you have is what we refer to as ZOS hybrid batch processing. We talked about what goes into the process of hybrid batch processing, and we've given you some demonstrations of how that works. The load balancer is an additional component to the COSY coprocessing toolkit that can be used to distribute that hybrid batch work to selected VBX virtual servers based on their relative workload weights. I should mention that the COSY toolkit is free to use under a community license, but that you can also purchase commercial support contracts for the product if you have specific SLA requirements that you need to meet. We have two different levels of contract. We have a silver level and we have a gold level, and the gold level provides 24/7 SLAs along with specific software indemnity requirements. Finally, you can visit our website at dovetail.com for more information on the COSY toolkit and the load balancer. All right, well, thank you very much for joining, and I hope this was informative and gives you a little bit of a picture of how the COSY launcher integrates nicely with IBM's zEnterprise, new zEnterprise systems, and how the load balancer can be used to move work around in that kind of ensemble. Thanks for joining.